So I'm going to talk about Gowers' uniformity of primes in arithmetic progressions. Most of what I say joint work with Joni Teravainen from Oxford. So I actually prepared two versions of this talk. One version is this slide that I'm going to go through. There is a second version, which is a one-sentence version of the talk for experts. So here that goes. There is a classical Bombieri-Vinogradov theorem about equidistribution of primes in arithmetic progressions with level of distribution 1/2. Our result is a refinement of that, showing that primes in arithmetic progressions are Gowers uniform with a positive level of distribution but less than 1/2. So in one of the most general results, the level of distribution would be one quarter instead. Okay, so that's basically a summary of the result. Of course, I'm going to explain what the background is, what the precise results are, and some of the applications. So let me begin with some backgrounds, recalling some classical results on the distribution of primes. Actually, this is going to share some common themes with the talk last week from Nikos. So my main goal would be to understand certain distributional properties about primes, or about Mobius functions, or about multiplicative functions in general. So lambda would be the von Mangold function, which is basically a weighted indicator function of the primes. And mu would be the Mobius function, which takes value plus or minus 1, depending on the parity of the number of prime factors. So the classical prime number theorem says that we can count the number of primes up to a threshold capital N asymptotically with an error term that saves an arbitrary power of log. So an equivalent form of this prime number theorem is that when you consider the partial sum of the Mobius function, you get cancellation, again with an error term that saves an arbitrary power of log. So it's known that these two versions are equivalent, and the reason I want to state this for both von Mangold and for Mobius is that in many of the results I'm going to discuss later, there is one result for the von Mangold, there is a corresponding result for the Mobius, but the results for the Mobius function are usually easier to state because there is no main term involved. So one is, in classical analytic number theory, one is interested in distribution of primes in arithmetic progressions modulus Q, and we want to understand the distribution for Q as large as possible. In that respect, we have the Ziegler-Wolfe theorem that says that as long as Q is up to log n to an arbitrarily fixed power, then one can count the number of primes in arithmetic progressions modulo Q and get an asymptotic formula. So this restriction on Q is unsatisfactory. The folklore conjecture is that such equidistribution should hold as long as Q is up to n to the 1 minus epsilon. Even assuming the Riemann hypothesis, actually there is a missing word here. Assuming the generalized Riemann hypothesis, one can show that the estimate above holds for Q up to n to the 1/2 minus epsilon. So even assuming the generalized Riemann hypothesis, we would be more or less halfway. We're only halfway towards the folklore conjecture. Unconditionally, we have the well-known classical Bombieri-Vinogradov theorem, which more or less says that this estimate above, holds true on average over Q. The expression inside the absolute value sign here is supposed to be the counting of the primes in A mod Q minus the main term, so it's supposed to be the error term, and the sum over all Q up to n to the 1/2 minus epsilon is representing an average over the moduli. So in words, the Bombieri-Vinogradov theorem says that primes are equidistributed modulo Q for almost all Q up to n to the 1/2 minus epsilon. So this is the result that we're going to study further later on. Another classical topic about sums over primes are concerning exponential sums over primes. So here we have, again, a classical result of Vinogradov in the case of the von Mangold and Davenport in the case of the Mobius function. If you look at the sum of the Mobius function twisted by this linear exponential phase function, e to the 2 pi I n alpha, then one can expect cancellation. So note that when alpha equals to 0, this is a special case of the prime number theorem, but for other values of alpha, this is different. So in words, this says that the Mobius function discorrelates with linear exponential phase function. So there is a similar result for lambda. I'm not explicitly stating it here because the result for lambda will depend on whether alpha is a major arc, such as alpha equals to 0 or alpha equals to 1/2, etc., or whether alpha is a minor arc. In the case when alpha is a major arc, there would be a main term when studying the Mangold, but for Mobius, there's always, the main term is always 0. So there are various motivations for studying such exponential sums. Here are some classical applications. If you can understand this sum, exponential sums over the von Mangold, you can prove Vinogradov's 3' theorem via the circle method. Similarly, one can get an asymptotic formula for the number of 3-term arithmetic progressions in primes, again via the circle method. But there are other applications, such as studying certain Diophantine approximation problems with prime denominators, etc. Okay, so the main thing I want to talk about today is kind of a hybrid of the Bombieri-Vinogradov theorem and a generalization of exponential sums of this type. And this generalization of exponential sums concerns Gowers' uniformity. But so let me quickly recall what the basic definitions are in this context. So if you have a function f on a cyclic group Z mod nz, or an interval from 1 to n, I'm going to abuse notation and think that they're the same thing. The UK norm of that function is defined in terms of this formula. I'm not going to go through this in detail, but in the case of U2 norm, this is the formula. So the force power of the U2 norm is the average over this expression, where x0, you can think of x0 as one vertex of a parallelogram, x1 and x2 as the length of the two sides of the parallelogram, and then these four numbers, x0, x0 plus x1, x0 plus x2, x0 plus x1 plus x2, are the four vertices of the parallelogram. So this is the average over all such parallelograms. So it's known that one can easily show that the U1 norm is the same as the L1 norm. The U2 norm is related to the Fourier transform of the function. So the U2 norm is the L4 norm of the Fourier transform. So these uniformity norms were introduced by Gowers to study Zamoreti's theorem in combinatorics. And they show out because of results like this for the generalized von Neumann theorem. If you want to count k-term arithmetic progressions n plus d, the dot n plus k minus 1 to the d, weighted by these functions f0, f1, the dot f k minus 1. By repeated application of Cauchy-Schwarz, one can show that this count is controlled, is bounded above by the uk minus 1 norm of each of the functions fi. So for 3 APs, this is controlled by u2 norm. This matches the fact that 3 APs can be analyzed using the circle method, i.e. using the Fourier transform. So in words, this theorem, the von Neumann theorem, says that KAP is controlled by Gowers UK minus 1. So basically, if you've not seen this before, UK norm for larger values of K are sort of a higher order generalizations of the classical Fourier analysis. And they are needed if one wants to study more complicated linear patterns, such as longer arithmetic progressions than 3-term. So to actually to analyze Gowers norms of a function, so eventually we might be interested in Gowers norm of a function, such as the Mendel function, such as the Mobius function, etc. To analyze them, there is a deep inverse theorem for the Gowers norms. The qualitative version due to Green-Tao and Ziegler in 2012. Which identifies basically abstractions to Gowers uniformity. So if you have a function f which is one bounded, meaning that its L infinity norm is bounded by 1, if its u s plus 1 norm is at least delta for some positive constant delta, then it must be the case that your function correlates with psi, where psi is a s-step neo sequence with bounded complexity. So the neo sequences are going to be defined on the next slide. For the moment, let me just say that if you look at the s equals to 1 case of the theorem, when s equals to 1, this is about the u2 norm, and it will be the case that the one-step neo sequences are precisely these linear exponential phase functions. So for s equals to 1, this is just classical Fourier analysis. If the u2 norm is large, then your function f has a large Fourier coefficient. So recently, there is a result of Manners that gives quantitative bounds for this constant C of delta and also this complexity. But because I'm not going to go into the issue of complexity, let me ignore that in this talk. So the bound he gets is doubly exponential. So it's worth mentioning that in the previous result of Green-Tao Ziegler, there was no quantitative bound obtained. So at this point, I hope you agree that if one wants to study combinatorial problems, the theory of Gowers norms shows up. And if one wants to study Gowers norms of certain functions via the inverse theorem, one would like to study such sums of your function twisted by neo sequences. So this provides motivation for studying sums of arithmetic functions twisted by neo sequences in various contexts. Are there any questions so far? Okay, if not, let me move on to the lazy definition of neo sequences. It's lazy in the sense that I'm not addressing the issue of complexity. But on the other hand, for the latter part of the talk, you don't actually need to know the definition. But if you do want to know, here is what they are. So first, give yourself a connected, simply connected nilpotent Lie group of step at most D, the D here is, sorry, the D here is supposed to be the same as the S in the previous slide. So this is the definition of a D-step neo sequence, or a neo sequence of degree. So easiest example is R to the G is equal to R is an example of a one-step neo sequence. The Heisenberg group is an example of a two-step neo sequence. G equals to R is a one. G equals to R is a nilpotent D group of step 1. The Heisenberg group is a nilpotent D group of step 2, etc. And inside of it, there is give yourself a lattice. For example, Z, the set of integers, is a lattice in R, the set of reals. G is going to be a polynomial sequence taking values in your Lie group. Think about classical polynomials and somehow adapt. Somehow there is a definition of polynomial sequences that take values in general Lie groups as well. And let your capital F be any nice function or Lipschitz function on the quotient G mod gamma, which is called a neo manifold. And your neo sequence will be functions of this form: psi of n equals capital F of G of n gamma. All right, so this is a definition, but the main thing that you might want to remember is simply that as special cases of neo sequences, one has the polynomial phase functions. If G is a polynomial where these alpha d, alpha 1, alpha 0 are real coefficients, and your function is psi of n equals e to the 2 pi I G of n, this is a polynomial phase function where the phase is degree d. This is an example of a neo sequence of degree d. So when d equals 1, this is just a classical linear phase function. And the other thing is that these things are not the only neo sequences. There are other things. A famous example is this expression called a bracket polynomial. This is a neo sequence of degree 2, and it's not one of the classical polynomial phase functions. Okay, so as I said, for the purpose of this talk, it suffices to just think of neo sequences as these polynomial phase functions. So for the specific functions of our interest, for example, the Von-Mangold and the Mobius, in 2012, Green-Tao established that the Mobius function discorrelates with any fixed neo sequence. So this can be thought of as a vast generalization of Davenport's result that works for psi being the linear exponential phase. So once one has that, via the inverse theorem for the Gowers norms, one can immediately deduce as a consequence that the Mobius function has UK norm little o of 1 for any k. Again, one can establish similar results for the Von-Mangold, but this becomes much harder to state explicitly because of possibility of a main term if psi is not in quote-unquote minor arc. Let me also mention a result of Franziginackis and Host. Their result concerns multiplicative functions, of which the Mobius function is a special case. So if f is any one-bounded aperiodic multiplicative function, then the UK norm of f is guaranteed to be little o of 1. But here a function is called aperiodic if this estimate holds for any fixed Q and A. So basically, if f is orthogonal to any fixed periodic function. So you can see that Franziginackis and Host's result implies the UK norm of Mobius being little of 1 as a special case, because this estimate certainly holds when f is equal to mu. This is the classical prime number theorem in arithmetic. but their result holds true for any other aperiodic multiplicative functions as well. So the reason I want to mention this is that somehow, if you compare what goes into the proof of this result and the proof of this result, there's less information about, there's less arithmetic information involved in the proof of this result, which is probably not surprising because it applies to more general multiplicative functions. Such feature will show up again at one place later on. Okay, so I think this finishes the an overview of the classical results in this kind of direction and provides some motivations. So let me now begin by mentioning some new results. So let me first start with the summary. So here is what we want to study. So we want to have a hybrid version of the Bombieri-Vinogradov theorem and the Green-Tao theorem about discorrelation with new sequences. So we want to look at Gowers uniformity of primes in almost all arithmetic progressions. So let capital Q be an upper bound for the moduli. We want to show that for almost all little q up to the threshold, I have this estimate about discorrelation of Mobius with new sequences in arithmetic progressions modulo Q. And I want this upper bound capital Q to be as large as possible so that I treat as many moduli as possible. So precise results will come in the next slide, and I will also discuss a few applications. The first application is rather straightforward via the machinery involving the generalized von Neumann theorem and the inverse theorem for the Gowers norms. Once I had that, I would be able to count the number of KABs in primes restricted to these congruence classes A mod Q from almost all Q. I can also show the existence of versions of almost twin primes in Bohr sets. I will explain what they are in a moment. And finally, this is a work in progress. I will again mention this in more detail later on. We can look at problems involving linear patterns in these almost twin primes. Okay, so now let me show you the precise version of this result. So as I mentioned in the introduction, maybe I didn't mention, but let me mention it now. This exponent 1/4 or the corresponding exponent 1/2 in the Bombieri-Vinogradov theorem is called the level of distribution. So if Q, okay, so this result says that for almost all moduli up to n to the 1/4 minus epsilon, I have this. I have this estimate which is precisely what I wanted. So I can estimate Mobius twisted by new sequences restricted to arithmetic progressions. So in this result, the residual class A and the new sequence psi is allowed to vary with the modulus Q. So the non-satisfactory thing about this result is the level of distribution 1/4, which falls short of 1/2, the one in Bombieri-Vinogradov. So this is what we can do. So if you only care about the new sequence being polynomial phase functions, then this is what the result says. You can take any residual class A, any coefficients alpha d and alpha 1, and for most Q, you will have cancellation for this sum of the Mobius twisted by the polynomial phase function restricted to this arithmetic progression. So we can improve this level of distribution 1/4 if in certain cases. So this will be the content of theorems 2 and 3. If psi, the new sequence psi is fixed, i.e. does not depend on the modulus Q, then we can improve the level of distribution to 1/3. Furthermore, if psi is a fixed new sequence, doesn't depend on Q, and furthermore, if the absolute value sign is replaced by a coefficient lambda Q, which is what's called well-factorable weight in sieve theory. I'm not going to go into details about this definition. And also, if the residual class A is fixed, such as 1, but it doesn't have to be 1. But A needs to be fixed, not depending on Q. If these are the cases, then we can get level of distribution 1/2. So I'll say more about this level of distribution business in a moment, comparing some of these results with with previous results without the new sequence. But before that, let me mention the applications first. So I'll mention the 3 applications referred to earlier. First, one can show that the set of primes that are A mod Q is Gowers uniform for almost all Q out to n⁴. This is a direct application of theorem 1 that has level of distribution 1/4. Corollary 2 is finding almost twin primes in Bohr sets. So here is the precise version. Let P be a polynomial whose leading coefficient is irrational. Let rho be some small positive number. And this is the kind of Bohr set I am looking at. The set of all integers n such that the fractional part of P of n is less than rho. So this is a higher degree version of the linear version of Bohr sets. So one can show that this, first of all, one can show that the set of primes in B has bounded gaps. So this is in the spirit of recent works by John and by Maynard on bounded gaps between primes. And this corollary would follow from a general result of Maynard about establishing the property of having bounded gaps in primes in general sets. And it turns out that one of the analytic input for establishing this is precisely the sort of, is precisely the theorems 1 or 2 that I mentioned previously. In a similar direction, we can also show that this Bohr set B contains Chen primes. So these are the primes P with the property that P plus 2 having at most 2 prime factors. The infinitude of these kind of almost twin primes was established by Chen, hence the name. Okay, so the third corollary, let me begin with a little bit more background. So this concerns the Green-Tao result about linear equations in primes. If you have L1 through LT, which are T affine linear forms in D variables, x1 through xd, with the assumption that no two of them are linearly dependent when you ignore the constant terms, then one can establish this Hardy-Littlewood conjecture. In other words, one can count the number of x in the box with L1 of x, L2 of x, all being prime. One can get an asymptotic formula for that, where the leading coefficient beta is basically a product of local factors that will depend on the coefficient of the linear forms. So this is a very general result, but a very well-known special case is you have these k affine linear forms in two variables x1 through x2. And in this case, the Green-Tao result stated here gives an asymptotic formula for the number of k-term arithmetic progressions in primes. So with our theorems 1 and theorem 2, we hope to establish the following corollary, which is an ongoing work joint with Pierre Bienvenu and Joni. So the goal here is to study an analogous version of the previous result, but with the requirement of being primes replaced by being almost twin primes. So here is a model case of such a result. If I let P be the set of Chen primes, again, this is the set of primes P, so that P plus 2 is a product of at most 2 primes. Then I can consider counting the number of variables x such that L1 of x dot dot LT of x are all Chen primes. We won't get an asymptotic formula, but we will get a lower bound, which is the correct order of magnitude. So if there is a constant c here, which is an absolute constant, there is another constant beta here, depending on the linear forms. It may be a little bit weird that I'm not combining them together, but this is just because the constant beta could be 0 if the linear forms have if the linear forms represent local obstructions. But otherwise, this c times beta is just one constant. So in particular, this would imply the existence of x, so that L1x to LT of x are primes, and L1x plus 2 dot dot LT of x plus 2 is missing here, I apologize, are almost primes, so product of at most 2 prime factors. So of course, what we would conjecture is that I can look at all of these 2T linear forms together, L1 of x dot dot LT of x, L1 of x plus 2 dot dot LT of x plus 2, and the Hardy-Littlewood conjecture would predict that, assuming that there are no local obstructions, the 2T linear forms can represent primes infinitely often. But this is something that includes the Goldbach conjecture and is, I guess, out of reach of current techniques. This result will mean that if we only want these T things to be almost primes, then this can be achieved. So if one wants to try to apply this to the case when the linear forms correspond to the k-term arithmetic progressions, this would imply that there are infinitely many k-term arithmetic progressions in Chen primes. But this result about KAPs in Chen primes was actually already known due to Zhou using techniques of Green-Tao. But our theorem here would provide new applications when the linear pattern involved is not what's called translation invariant. KAPs is the pattern of KAP is an example of a translation invariant system. If you translate a KAP, it remains a KAP. But if that's not the case for the linear pattern, then this is a new result. Okay, so I stated the main results. I discussed applications. I promised to say a few words about the level of distribution. So here is a summary of the situation. D is the step of the new sequence. So D equals to 0 corresponding to the classical Bombieri-Vinogradov case, no twist. D equals to 1 is one-step new sequence, so that's linear exponential phase. So this is basically exponential sum version of the results. And the general psi is the theorem 1, 2, and 3 that I stated. So the 3 rows correspond to the situation in theorems 1, 2, and 3. Theorem 1 is the most general situation. Theorem 2 is with the fixed new sequence psi. And theorem 3 is a fixed psi with a well-factorable weight and with a fixed residual class A, such as A equals to 1. So in our general result, the level of distribution in the three cases are 1/4, 1/3, and 1/2. So here are some previous results for twists by exponential, for twists by linear exponential phases. So let me just recall for you the classical results without twists. So for the first two rows, you have the Bombieri-Vinogradov theorem, which gives 1/2 level of distribution. In the last case, when you have this well-factorable weight with a fixed A, there is a result, a famous result of Bombieri, Friedlander, and Vaniak, that in which one can go beyond the 1/2 barrier, and going beyond the 1/2 barrier is an extremely important subject in analytic number theory. So some natural questions can be asked about these. Can these two be 1/2? Can this be bigger? So even in this case of exponential sums, these questions can already be asked. So, but let me mention a few things about this. So first of all, there are later results in this regard about breaking the 1/2 barrier. One appeared in the work of Jan on establishing bounded gaps between primes. So there is a result established by him of this nature. And very recently, there is a series of papers by Maynard, which breaks the 1/2 barrier in the Bombieri-Vinogradov problem without the need for a fixed residual class, and without the need for the well-factorable weight, but with some other more mild conditions on the moduli Q. Okay, so these results are recent and potential breakthroughs in this regard, so I thought I'd mention them. The other thing I want to mention is that when you have this twist by new sequences, for the Mobius function, we can actually get to the level of distribution 1/2 if we can accept a weaker error term. So in all of the results I mentioned earlier, all the error terms, you get a saving of an arbitrary power of log. But this result only saves log n to the 1 minus epsilon. And it only holds for the Mobius function. So there is no analog of this result for the von Mangold function. So this also, the proof of this result builds on work of Green about the Mobius function in arithmetic progressions without the new sequence psi, where he's able to break the 1/2 barrier for a fixed A. Okay, so this is some issue about about level of distributions. Let me finish the talk by mentioning a few ingredients in the proof. So I will try to just focus on theorem 2, which assumes Q is up to n to the 1/3. And I have a new sequence psi, which is fixed. I have the residual class A mod Q, which might depend on Q, so I'm putting a subscript Q here. And my goal is to establish this. So there are 3 steps. The first step is to reduce to the case when the new sequence psi is equidistributed. So in the case when it is E of alpha n, or alpha n to the k, this just means reduce to the case when alpha lying in minor arcs. One can do that basically because when alpha is major arcs, this follows from the classical Bombieri-Vinogradov. And to deal with this step for general neo sequences, one needs to use the decomposition theorem for neo sequences due to Green-Tao, due to Green-Tao. So now assume that psi is equidistributed, so we're in the minor arc case. Step 2 is to use Vaughan's identity to get rid of the Mobius function, to reduce the matter to proving a type 1 sum and a type 2 sum. And the step 3 is then to estimate this type 1 sum and type 2 sum. And the estimate uses, as you would expect, Cauchy-Schwarz. And if one were just to look at these exponential phase functions, then one would use the Weyl inequality for such exponential sums. For general Neo sequences, one would use generalization of Weyl inequality, basically, again due to Green-Tao. So from this summary, you can see that the proof of our theorems is more or less combining known techniques in analytic number theory, such as using Vaughan's identity, with known machineries in the theory of Neo sequences. There isn't really any innovation going on, so there is potentially room for improvement, particularly if one wants to improve the level of distribution. So as you can also see, step 3 is the main part. So I'll try to tell you what type 2 sums look like and tell you why 1/3 is what we can get. So I have this side and the next one that tries to explain this. So the type 2 sums will look like this. Basically, the original Mobius function mu of n is replaced by a product of two things. An and Bn are two sequences supported on capital N and capital N respectively, where the product of m and n is x, and they are between x to the 1/3 and x to the 2/3. So the powerful thing about using Vaughan's identity to reduce matters to this is that now one has two variables. Now this is a bilinear sum, and one has two variables, so there is room to use Cauchy-Schwarz inequality to proceed. The other powerful thing is that the mysterious Mobius function that originally appeared now goes away. So here we just want to treat this for arbitrary sequences Am and Bn that are essentially bounded by 1. So if you pull out the sum over m and just get rid of Am, you get this upper bound for the sum. Now you Cauchy-Schwarz. So when you Cauchy-Schwarz, this absolute value will get a square, and you will expand that square. So you will get two copies of the variable m. So it will basically look like sum over these two copies of n, and then sum over m with m times n congruent to aq, and also n times n prime congruent to aq, which would imply that n is congruent to n prime, not q. And then this condition remains. And then the Bn after Cauchy-Schwarz can also be thrown away. And then I get psi of mn times psi of mn prime bar as the sum. So I can already explain here why the level of distribution 1/3 occurs. This is because if you look at the inner sum, the length of the inner sum, the length of the side of the m variable is capital M, and you have this mod q restriction, so the length of the inner sum is capital M over q. I certainly want this sum to be non-trivial, so I want my q to be smaller than capital M, and capital M can be x to the 1/3, so I want my q to be up to x to the 1/3 minus x2. So this is the reason why we get 1/3 in the exponent here. Just to say that as long as you have this assumption, you can actually estimate this. So here is where you can proceed from this point on. So this is the copy of the inner sum appearing in the previous expression. you have a sum over m with this congruence restriction, and the summand looks like this. Let's just look at the special case when your psi is a polynomial phase function. In this case, the summand looks like this. And recall that this is the sum over m congruent to something mod q. This is something that can be estimated by the classical Wales inequality. So this sum should be, we should get a cancellation for this sum unless alpha times q to the k times n to the k minus n prime to the k lie in appropriate major arcs. So alpha times n to the k minus n prime to the k is basically the frequency appearing here. There is an additional q to the k because n is restricted to something mod q. Okay, but so this is the inner sum that appears in the previous slide. And if the whole expression is big, then this is going to be big for many q and n prime. So in other words, this expression is going to be in major arcs for many values of q, n, and n prime, satisfying certain conditions. You can imagine that one can, this is the Diophantine problem that one can solve to conclude that this is the case, then your alpha should be in major arc. But that's a contradiction because I already reduced to the case when alpha is in minor arc or psi is equidistributed. This is the rough strategy of the proof. To treat general null sequences, at this step, one would use a quantitative Kronecker theorem to deal with this kind of sums over null sequences instead of Wales inequality, but the idea is the same. Okay, so I think this finishes my talk. Thanks for listening.